Um, wow, that was a great morning talk. I don't know if that was coincidental, but I'm full of energy now. I have to cough. Excuse me. Our next speaker is Bordeaux, or Matt, or Matthew. I met Matthew when he was a young boy. No, 5 years ago, we were volunteered at CSS and JS Conf together. And it's pretty exciting that you're on stage right now. Matthew is a self-proclaimed coffee snob. Hello, I am too. And spends time watching The West Wing lately. What are you up to? What series?
So I won't watch past season 4. It just got bad after that.
Okay. Matt's currently working at as a site reliability engineer at Seer Medical. They're Australia's largest epilepsy diagnostic service. Seer diagnoses patients over 7 days of continuous monitoring of their brain activity at home. So that means they can stay at home and be monitored rather than a long stay in hospital, which is pretty great for people. Yeah, so he's working on something important, and we were having a chat at the coffee yesterday, and it was like, most of us can say if we put a bug into production that it's not, saving lives, but he's actually saving lives. So be a lot of pressure as a site reliability engineer on that team. But today, instead of helping people, Matt's going to talk about murdering Mongo in a slight diversion. So, welcome, Matt.
Today we're going to go on the journey of murdering a database. As Mel mentioned, I currently work at Seer Medical, diagnosing epilepsy. This project actually happened at Stile Education, where I was working last year. Stile is a highly engaging learning platform with diverse content that contextualizes science with the latest news and issues relevant to students. They teach physics with driverless cars, chemistry with chocolatiers, and biology in the context of the 2014 Ebola crisis. They recently published a lesson exploring the science behind the recent bushfires and the contribution of climate change towards them. So before we get into murdering Mongo, I wanted to introduce MongoDB for those of you who might not have used it before. Mongo is a document-based data store, which means that you can write to it directly from your application by serializing existing objects into JSON. Whereas in a traditional database, you might use SQL to write data into data structures that you've already predefined with a schema. In Mongo, there is not necessarily a schema, and you write into it using its own query language. It has support for sharding data over multiple servers, meaning that you don't require one large server to store all your data. And it's usually deployed in a set of 3 or more servers for high availability, with one primary server and multiple secondary servers replicating data from the primary. So there's some trade-offs to picking Mongo as a database compared to a relational database. It recently got transaction support, but up until recently, you had to implement transactions yourself through strategies like two-phase commits. It now has schema validation, but updating the schema doesn't affect data that you've already added to the database. And it's not well designed for relational data. It doesn't have features of a relational database, like foreign keys to enforce relationships between records, or joins to connect documents to each other. So when considering Mongo as a database, it's worth asking yourself if the nature of the data that you're storing in there is well suited to Mongo, and if these trade-offs are right for your application. So today, I'll explain why Stile introduced MongoDB as our second database. I'll share some example of use cases we had for Mongo throughout its life, and I'll share the process that we went through in deciding to remove Mongo from the application. And I'll deep dive into how we safely refactored Mongo out of our code base and knew that it was really dead to our application. So I want to tell you a story. It starts back in 2011. This was before I joined the company in 2015. The original application was built in PHP, and they didn't have any real customers at the time. But as they started to get some, they knew that they didn't want to continue to write the application in this spaghetti code of PHP. And so they asked themselves this question: if we started again, what technologies would we choose? And the developers, not having a lot of experience in designing technical applications, or being recent graduates from uni, decided to look through the catalog of application design on Hacker News. And at the time, MongoDB was highly popular, and to the founders of the company, it looked like the database of the future. It also looked like it would have solved some of the problems that they'd previously encountered with MySQL. The previous experience of one of the founders using some of these older versions of MySQL was that they didn't have support for transactions, suffered referential integrity issues, and were optimized for read-heavy operations, whereas this application was going to have a high write workload. So Mongo also made an appealing case for a high availability clustered database at a time when there were no solutions for clustering MySQL. So in 2012, they rewrote the application as a set of 11 Ruby microservices communicating over a message bus. This allowed each microservice to choose which database it wanted to use, Mongo or MySQL. But when they were doing this migration, they'd written the first version of the application using MySQL, and they didn't want to take the time to migrate the data over to Mongo. And they'd had a lot of experience using MySQL in the past. So they decided that they'd use both Mongo and MySQL. In this new web-scale architecture, some services used Mongo and some services were using MySQL. But due to the lack of previous experience with Mongo and a few early outages, they tried to keep only non-critical data in the Mongo services. However, this led to some issues when coupling was introduced between the Mongo services and the MySQL services. So they came up with some makeshift ways to reduce this coupling. When you'd make a call into the auth service up the top, it had to call over to the email service to find a user's email. So someone introduced a Redis cache in the auth service so that if Mongo was down, our MySQL services wouldn't have been down. And we spent a lot of time trying to implement things like this to keep Mongo from affecting our use of MySQL. However, every time we had an incident that involved Mongo, we'd find a new way that we'd coupled these services together. So for a long time, we had more microservices than developers. And in 2017, we abandoned our microservices architecture in favor of a monolith. Rather than everything having to call through this centralized message bus, they could now just make calls through the same process. So this introduced some new complexities around managing connections to two databases within one application. Unlike the previous architecture, where if Mongo was down, the site was ideally up. In this new architecture, if Mongo was down, the application wouldn't start, and our site was fully down. So throughout this journey, we didn't really have an impetus for using a second database. There wasn't a technical problem that we were solving with it, and we really could have implemented the same APIs using MySQL. The advantages that Mongo presented weren't really advantages for our application. And so, as we began to rely on Mongo, we had to mitigate some of the issues with it. When we first introduced it, there were no hosted services for it, and we were running our own Mongo cluster on EC2 instances on AWS. And this meant dealing with all the challenges of running a database yourself. Setting up Mongo and getting its defaults correct, capacity planning. At one point, we scaled down the database over the school holidays and forgot to scale it up again until school went back and all our users came back online, taking the site down on the first day of school. We also had to maintain all our own backups and monitor the cluster. So in one case, we were doing some maintenance. We'd been running our Mongo cluster on servers using EC2 Instant Store. If you've used storage volumes on AWS before, you'll know that EBS volumes can survive longer than the lifetime of the instance they're attached to, sort of like an external hard drive. Well, instance store is different. The storage of the instance only survives as long as the instance is turned on. More kind of like a computer that deletes everything when you restart it. So this provided some fast ephemeral storage, but it wasn't ideal for persisting a database. So during an upgrade, one of these 3 Mongo servers was shut down by an operator who thought they could just take the volume and reattach it to another server. But when the operator shut down the instance, it deleted all the data that was on the volume. Fortunately, the other Mongo servers had a full copy of the database, and we were able to copy over the database to a new server. But this caused a few hours of downtime while we resynced the data. So Mongo had saved the day with its replication of data to multiple services. But the fact that we needed to do these kind of database upgrades ourselves required specialist knowledge. And we had a few other outages from Mongo. Most of these were application-level outages due to the lack of schema. After applying updates to code, our new code wouldn't work with the existing data. And then we had one big outage. And this was what really killed Mongo. Our metrics server, Prometheus, would ask our application every 15 seconds to ask Mongo for the size of a collection. This caused a fight when this collection scanning started to take longer than 15 seconds. And these collection scans started to happen in parallel. So the metric server kept asking, our application kept making more and more connections. Eventually, the Mongo server had over 1,000 concurrent connections all running these parallel connection scans. And as Mongo got slower, it dropped some connections. But creating new connections is expensive in Mongo. So as the connections were dropped, new ones would be created. Now, I need to take a minute to explain what the load average of a server is. The load average is the time waiting for a thread to be processed. You look at the load average on your computer, and it's usually between about 0.5 and 2. And the load average on any server should usually be less than the number of CPUs on that server. A Mongo server had 8 CPUs. Here's the load average on our Mongo server at 1,500. So this was caused because when those connections were dropped, the Mongo Ruby driver would automatically and instantly retry to recreate all those connections. So you can see the big spike at the end when Mongo recreates every connection that it had open. So this set our whole cluster on fire, because when one server went down, we couldn't continue our configuration was set to stop accepting writes into the whole cluster. This illustrated to us that we really hadn't spent a lot of time setting proper connection limits for our application. And we hadn't set proper connection limits for our Mongo server either. We had a long discussion about if we should invest more effort into getting these types of default settings correct for Mongo. But given it had taken us years of testing our MySQL settings in production before we became confident in them, we decided to opt towards the path of removing Mongo and double down on our investment in MySQL. So there were some other issues that we've encountered using Mongo. And one of them was that we didn't use an ORM. We weren't using a framework like Ruby on Rails, and we needed to implement all the database interactions ourselves with the Ruby driver for Mongo. This added a whole extra burden of creating an ORM-like framework that we'd written ourselves. So because Mongo didn't have a schema, we tried to create one. We wrote these YAML files that defined the collection and the type of data we were storing in it. And then we'd use this to code generate Ruby models. We'd also code generate all the ORM for each collection. And these code-generated repositories were an abstraction between our API code and Mongo. But they quickly became difficult to manage because it was very difficult to regenerate these files after developers went and made manual edits to them. We ended up with what looks like the same file, but with many different functionalities and behaviors. And we found that the cost of auto-generating these models allowed us to write code very quickly, but then was very expensive to maintain. So after years of living with Mongo, we decided that Mongo wasn't providing us with any advantages over using our existing MySQL database. We'd invested more deeply in our knowledge of growing and running MySQL, and it had the advantage that it was on a managed service by AWS. We really didn't need the burden of running another database ourselves. We first considered moving to a hosted Mongo service, but by removing Mongo from our application, we were able to simplify the technical design of our application. So once we'd decided we wanted to remove Mongo, we needed to do it without downtime, ensuring that we didn't lose data during the migration. First, we defined a MySQL schema that fitted the shape of the data that we were storing in Mongo, and dealt with the possibility that data was missing from existing documents. Next, we needed to migrate the data. So we could have done an offline migration, where you turn your application off, migrate all the data across, and then turn your application back on again. But what happens if the migration doesn't work? If you wrote corrupted data into MySQL? You wouldn't have found out until you turned your application back on and it didn't work. But now you've started accepting writes again. And so now some data exists in MySQL that doesn't exist in Mongo. So you could try and reverse migrate back, but it's probably 3 a.m. when you're applying this migration, and you definitely didn't write a script to transfer data from MySQL back to Mongo. So instead of this method, what if we could do a migration in small steps that we could rewind if it went wrong? So we first write records into both Mongo and MySQL. We also perform updates and deletes on records in both databases. And the advantage of this dual writing approach is that you're able to continue to use your old database while you're migrating to the new database. So we'd first write a record into MySQL, then into Mongo. Now both databases have both records. We're now able to continue to run our application on the old database without any interruption. We used a script to fetch records from our existing Mongo database, and we just did this all through our API. We'd then dual write them back to the database using the insert method that I just showed. So now we're able to migrate all the records that don't exist in MySQL and copy them over to Mongo. If the migrations went wrong, you're able to delete all your existing data in MySQL and do it again. While this is happening, you're still accepting writes into both data stores. So now we need a way to change over where we read from. We could do something like this, where we switch over from reading documents from Mongo directly to reading documents from MySQL. But how would we know that the data in MySQL is correct and that we haven't stuffed it up? Well, we could run our tests. We could run them with the Mongo implementation and then run them again with the MySQL implementation. However, all our test data is freshly created on each test run, and it isn't representative of the data that we've created over many years with many versions of the Mongo schema. If we'd messed up any of the migration code that was copying old records to MySQL, we wouldn't have known until after we'd switched over to reading from MySQL and returned that invalid data to real users. So what if we could test this in production? Well, it turns out we can. Using a tool called Scientist from GitHub, we can safely refactor our code and execute it before real users see it. So we replaced all existing Mongo methods with a call to Scientist. Scientist will always call our Mongo method and return the result. But then it will try our MySQL method on a small percentage of requests. This allows us to incrementally increase the amount of reading we're doing from MySQL to look for performance issues. And it allows us to compare the results that we fetch from Mongo and fetch from MySQL. And this is all inbuilt into Scientist. So when Scientist finds a mismatch, It will log the difference, and you're able to go out and figure out why this happened. Otherwise, this data would have been returned to real users, and we would have shown them deleted records. So this flow looks like this. A request comes in, we read from Mongo, read from MySQL, compare the two, return the response that we read from Mongo, and we just do nothing with the MySQL document. And it was a really good thing that we applied something like this, because we found two very critical errors. One was an off-by-one error on an index array that caused us to write the wrong value for the reliability field into MySQL. You can see that the counts of records with a bad reliability in Mongo and with a bad reliability in MySQL are really different. The other error we found was a bug in our MySQL configuration. The reliability field uses an enum, which is a strict set of values. When writing a value that's not in that strict set of accepted values, MySQL didn't raise an error. Instead, it just silently wrote the empty string without us knowing. Without scientists, we wouldn't have known about these issues. We would have just been serving this invalid data to real users. So, after we fixed these issues, we were able to migrate all the data across to MySQL again. And then, after a few weeks of running this approach with the dual reading from both databases and comparing the results, we were happy that the new MySQL code was consistently returning the same results as Mongo. And we were able to switch over to primarily reading from MySQL. We kept scientists reading from Mongo while we were running this new MySQL code. This allowed us to roll back at any time because all the records were still being written to Mongo. So switching over just involved flipping the experiment method over to being the control method. So now a request comes in, we read from MySQL, read from Mongo, compare the two, and return the response that we got from MySQL. If we needed to, we always had the option to switch back to reading from Mongo without losing any data. So now we needed a way to know that Mongo wasn't secretly lurking in the background without us knowing about it. We wanted to try our site without Mongo and make sure that it worked. So we invented this method called request cursing, where we added a HTTP header to requests to our API. And when our API would contact Mongo, a service unavailable error would be raised. This simulated a Mongo outage, but it would only simulate it for us. Here's a quick demo of request cursing in action. You can see that as we start to use the site, more requests are coming in, returning 503 service unavailable. So these things aren't breaking the page at the moment, but as we go back to the page we were previously on, it turns out you can't load that without our Mongo database. And so we were able to use this to to incrementally refactor parts of the site and confirm that they weren't using Mongo. The other method we used to find places that Mongo was still being used was Jaeger tracing. We wrapped all calls to the Mongo Ruby driver in a trace span, and this allowed us to get an understanding of where Mongo was being used heavily. So when we were confident that the migration was a success, after a few months of running it, we could simply just remove the Mongo code and remove the data from Mongo. Up to every point in this journey, we've been able to roll back to Mongo. And we've been running this for months using our MySQL implementation now. So this was a success. We'd migrated away one API from Mongo, but we had to repeat this process dozens and dozens of times, removing Mongo from many APIs. We started out with an easy API to begin with, but then picked a really difficult API to make sure that this approach would work for all kinds of data that we'd been storing in Mongo. But like all migrations, the tail end takes the longest to complete, and Mongo's still kicking around Stile. We hope to kill it off this year, as we've been gradually refactoring it out of our application. So today, we've looked at why we introduced our Mongo into our application when there wasn't a clear need for it, why we removed Mongo because of the burden it was causing us to maintain, and how we did it with safe refactoring using Scientist, and some of the key tools that we used in confirming that we didn't rely on Mongo anymore. So for me, this project was a reminder of the cost of adopting new software. It's quick and cheap, but the cost of maintaining it is expensive and occurs on a timeline of many years. So when you're evaluating a new piece of technology, have a plan for what will define success for it, and have a plan to be able to back out of it if it doesn't meet those goals. Because a half-finished migration is just technical debt. It'll give you the costs of both the old and the new state without reaping the full benefits of either. If Mongo really was the database of the future for Stile, then we should have fully migrated over to it. But the costs of having both databases increased over many years without delivering any value. So you might have thought this talk was going to be about Mongo, but really it's about how we simplified our application by removing a database that we didn't need anymore, and that was causing us more work to maintain than the value it was generating. Stile's been on a journey to refactor its application from a technical design that was intended for massive scale to a design that allows them to deliver software more reliably and with less maintenance burden. And I'd encourage you to discuss with your teams how you can simplify your own applications by questioning the need for technologies that aren't serving your ability to deliver useful software to your customers. Thank you.